Hamid, how are you?
Very good. Anas, would you like to say hello to
Oh, hey Anas, nice seeing you.
my camera? Sometimes my camera goes out. So, you guys hear me?
Yes, we hear you.
Okay.
And oh, okay. And I see Professor Rasulov.
Yeah, hello,
Whoa.
everyone. Just Meet's camera probably frozen. Got frozen. We can hear you, but your video is not moving actually.
Okay. Yeah, if I ever have to share my screen, that should work. It's just literally the camera that shows my face. Sometimes, I don't know, if it disconnects or something. I've had that issue before.
Yeah, hopefully your screen will be working well.
Yeah, it should.
How are you doing, Professor Killen? Everything fine?
Oh yes.
Things are
Yes.
okay.
Yeah, very good, very good. So we have about 2 hours, right?
Yeah, I don't know if you're gonna talk these 2 hours, but yeah, thanks for the reserving at least for this much time. Who knows how these things all move?
Okay, okay, but there is no conflict. You have time, and there is no schedule conflict until 4, right?
This time, no scheduled conflict. I have lots of other things to do, but no meetings at least between 2 and 4.
Okay. So let me suggest the following plan for your approval. We can let Mead to show his slides. We will ask him questions and maybe give some suggestions. And then after he's done, I will show some slides myself so that it probably will be good collaborative effort.
Would be great, yeah, would be great.
So please give me one minute. I just need to take coffee. I brewed it and I forgotten to take it with me here.
Yeah, that's a good idea. I also have to do that, yeah.
Okay.
Ready to go?
Yes. So if Mead wants to share slides, it is okay, but I can serve as a assistant and just show his slides, and Mead, you can just tell when to flip them.
Yeah, I should be able to share my screen. It's like just the part that shows my face. It's kind of have issues. I'm trying to see how we. Do you guys have to make me like presenter? Is that how it works? Oh, wait, there's share screen. Oh, okay. Never mind. Okay, you should be able to see my screen, yeah?
That's something different now, or that's what you wanted to show? Okay, well, yeah, we see the screen.
Yeah, you see my PowerPoint screen, right? Yeah. Okay, so clarification on what's going on. So the X's are complete so far.
What? Wait. What do you mean X's?
X.
Oh, symbol X. Okay.
Yeah. Or as complete as I understand them to be. Obviously, if Dr. Killen suggests something, I can redo them. But the X's are complete, and all these slashes are stuff that I've tried, but I having errors, and so every time I have an error and I'm unable to fix it, I send it to Dr. Killen. And so these are all the things that I've tried so far. It's all those slashes. So I believe, I'm not sure if you saw these density of states figures that I had before Dr. Razlev. Like we did the ground state stuff. And then I got some spectrums for Polymer 2 and dimer as well. Which, my question to you guys is, what is this, telling me? I'm still trying to learn this.
So you want to discuss, instead of presentation, you want a style of discussion, right?
Yeah, right, with this part, yeah.
Okay,
yep.
Okay. So, and I see that we have one more attendee. Dr. Yulun has joined.
Hello.
Hello, Yulun.
Hello, Yulun.
Yeah,
yep. Good to see you.
Okay, so Mead is asking how to interpret absorption spectra and why they're needed in this project. So,
does Dr. Han know what we're doing?
I think you can briefly introduce if you want. It may take like maybe 1-2 minutes.
Okay, Dr. Han, hello. Dr. Killen and Dr. Razlev have been greatly influential in starting a photodegradation project regarding monomers and polymers. And so I want to kind of explain what we're doing. This specific polymer, what we're going to be doing is highlighting that. And what we found in experimental studies is that it can be photocleaved or have photodegradable. And so what we're going to be doing is using the TDESMD process that you all have developed, and hopefully to study what exactly is happening with this photocleavage or photodegradation. So here's just stuff that I previously found, and here's kind of my to-do list that I'm currently working with Dr. Killen on. And so now I'm just showing the slides of what I've done so far.
Thank you.
Is that okay, Dr. Han?
Yeah, thank you.
Okay. Yeah, so like just initial density of states of the ground of 2 conformations, where I have them classified as monomer 2 and dimer, but in reality they're just different conformations. So here's the first one, here's the second one, and then I was asking Dr. Killen and Dr. Razlev if they could explain what exactly am I trying to see with the spectrum, and then you joined at that point. So could you guys explain to me if possible?
I hope. Mead, can you flip back to your table, like table with plans, with your X symbols?
Yes.
So, can you please explain how? What do you imply? What do you interpret? Sorry, it's my alarm, so that I do not miss this meeting. What is excited temp 1 and excited temp 2?
So temperature 1, I put it at 300 Kelvin, and then the email that I got from you today suggested that the largest one should be approximately 1 to 2,000 Kelvin. So this temperature 2 is at 2,000 Kelvin, and temperature 1 is at 300 Kelvin.
Okay, but what is excited?
I guess just high temperature. That's what I call it.
No. We should
okay.
Catch it and fix it right away. So
good.
Now let's flip back to your introduction slide, where you explain what is photocleavage.
Sure.
To the very beginning, when you introduce things.
Are you saying even like
first or second when you introduce what you did show to Dr. Han?
Okay, so like this one. Yep.
Yes, this one. So if we look at the top left panel, it does have two thick green arrows, curly arrows. And on the left curly arrow, you have a symbol H nu. Sun and symbol of H nu.
Yep.
Can you explain what it is?
That would be UVE radiation.
Okay. Good. So your polymer is degrading because of irradiation.
Yep.
What does radiation makes to the polymer?
It transfers energy to it.
In which form?
Well, light wave energy.
No. I read between lines that it is very highly likely that you may be under a little deception. That you are thinking, please correct me if I'm wrong, but I assume that you may have the following error in your train of thought, that light communicates energy to the polymer, and polymer accepts this energy, gets heat, and starts moving in higher temperature.
I wouldn't say heat, but it just gets excited because it's absorbing energy. Not
But
necessarily
okay.
Yeah.
So if I'm wrong, I'm very happy. But what do you understand under being excited? Not for humans, like we all are excited, but for the polymer.
Yeah, my understanding of excited is just having more energy in the polymer itself. It's absorbing more energy.
Please be more specific.
Yeah, when I like, that's the vague term. It could be heat energy. It could be light irradiation. It could be. It's just any type of energy.
Okay. So about light irradiation, how does excited state relates to the Fermi wave? Fermi keyword in the in-car.
Well, that was when we were moving an electron from HOMO to LUMO, or from HOMO to LUMO.
Very good.
So
Very good. So if you are fine with this concept, then you are safe. So the main idea of the project is to explore the polymer with this Fermi line in the in-car. When the model is photoexcited. Photoexcited means electron is promoted from HOMO to LUMO or from some other orbital, from HOMO -10 to LUMO +5 or whatever. This is a key. This is a heart of the project.
Exploring that different. What would you call them? Excited states, or what would you call those differences? Okay.
Yes, and the main idea behind everything is that in the excited state, bonds become loose, or bonds become obtain different equilibrium position. So the forces on atoms change when you photoexcite, when you apply this Fermi. And then if one does it in the right way, it leads to the breaking of the bonds and degradation. Now let's go back to your question about absorption spectra. Okay, so can you please tell how do you get the absorption spectra? Just briefly sketch the procedure.
I'm using something called OS strength, which I assume is oscillator strength.
Okay, good. Okay, very good. So
yeah.
What is inside this oscillator strength?
I'm not 100% sure off the top of my head.
So when you present next, we will try to cover it together right now, but when you present next time, please copy-paste the first several lines of the oscillator strengths just in the slides and explain what each column means.
Okay, one moment. Let me write this down.
Okay. So please figure it out yourself. But let me quickly bring this up in roughly. So approximately the file oscillator strengths has records corresponding to each peak in this spectrum. So each peak in the spectrum corresponds to a pair of orbitals, of one occupied and one unoccupied. And for each pair of orbitals, there is a energy offset between occupied to unoccupied, and there is a so-called oscillator strength, which shows probability that under photoexcitation, electron will go from occupied to unoccupied. Make sense?
Yeah. So this is the how would you say, the plot that kind of shows the probability
Yes,
of this occurring?
exactly,
Okay.
exactly, yes. And the spectrum is just visualization for humans, but for computers, oscillator strength is more than enough. And this information is needed to assess which pair of orbitals we want to promote into excited state with the Ferrier command in the in-car. So if if there is a high, tall peak in the spectrum, it means it has high probability to be excited. And it means in computational modeling, we want to figure out which orbital, which occupied and unoccupied orbitals correspond to this peak, and then to perturb them by the Ferrier command.
Okay.
Make sense?
Yep. Yep.
Okay, so please keep going. I think you stopped here, and now your question seems to be answered.
Yep. Yep. And then, so that was just the first confirmation. I'm going to have two confirmations, and then this is the second. So obviously you see the peak can be different. So clarification, we don't know, as of right now, we can't tell what orbitals are that transition, right, from HOMO to LUMO. These are just kind of saying we have to do more analysis to determine which orbitals have that peak. Is that correct?
For each peak, one needs to plot pair of orbitals, showing from which orbital to which one, and maybe to label, so to focus and analyze the spectra.
This was just a picture of showing me increasing the heat for what I was calling excited or temperature, but this is just for heat.
Okay.
300 Kelvin, 300 Kelvin.
Thermalized. Okay.
Yeah, thermalized. Yeah, that's a good way to put it. This is the density of states for heat of 300 Kelvin, first confirmation, second confirmation, and I did 2000 Kelvin for first confirmation and second confirmation. And I was unable to get the spectrums just due to some errors with wavecar files, which
do not worry.
I read a little bit.
Do not worry. We will fix this little things. But what may I ask? What is the difference between heating and molecular dynamics?
Heating and molecular dynamics. I want to say it's what's moving the molecules. One is the input of what we call heat energy, which is determined by some sort of calculation, whereas the other one is just like a molecular dynamics, what uses like Newton's laws, F equals ma, and we're calling like a ball and stick.
Super. Yeah. Enough. Very good. So the heating is just preparation of initial momentum for each initial velocity for each ion, and electronic structure at the end of heating is maybe good technical information, but it doesn't have much scientific value for end product. But what is important that after heating, one immediately should run molecular dynamics by copying the quant-car, the geometry and momenta inherited from heating into molecular dynamics.
Okay.
Make sense?
Okay.
And
Yep.
one more disclaimer. Molecular dynamics, when energy is communicated to the model in a form of heat, thermalized energy, is only a reference point. The main calculation will be when energy is communicated by applying this Ferrier code. So
Okay.
what you are showing is introductory path for like reference calculations. It's not the whole story.
Yeah, yep.
Okay.
It's just preparation. Okay.
Okay.
And yeah, that's all I have so far, just due to the errors that I was receiving. So,
Okay. So what are your next steps?
well, looking at the graph, well, for sure, molecular dynamics. There's two things I need to clarify with that is, the time step that we're trying to be using. I keep using your debug, Corey/debug, and I know that's just for like an initial quick run, but do you want me to be running it longer, everything longer than that?
Oh yes,
or
yes.
Okay.
Yes. I just give you warning so you do not overuse resources before you get a little confidence and experience. But please feel comfortable to go beyond this debug queue and use more resources. It is without resources you cannot complete the project.
Yeah. So yeah, what my understanding is, we can just pick like a number of steps and the time limit, and I would just submit my jobs and just always have that as a reference, because that way I don't have to change it ever. So you're saying what, 2,000 steps is a good number?
Wait. Let me bring up a little practical hint. There are two things. You or me as a researcher and petitioner are submitting job and asking for so many steps, but job scheduler and system administrator as a government of the NERSC cluster not necessarily will match what we request in the in-car. They will run the job for the whole time specified in this .sh script, debug sh or Corey.sh script. So it's very highly likely that the job will run only small portion of what you want, and then you will be cut off because of the regulations of the cluster. Sometimes it happens opposite. Everything you request is done before this limits expired, but you can some meticulous people compute it with calculator, but if you do it frequent, you get just general feeling how this resources and size of the system and number of steps in molecular dynamics relate. But those are different things. What you tell in the in-car, there is no guarantee that job scheduler will allow you to run so long.
Okay.
Good.
Okay. Well, yeah. Well, I just want to clarify. So if we have like a paper, I don't want to put 200 steps and be like, okay, we're good, and then we find out later that's not. Like, is there a bare minimum that we absolutely have to have that I need to be aware of?
2,000.
2,000 is the bare minimum.
2,000 steps and about 24 hours all time.
Okay. Well, I will make sure I always have that. Okay. Thank you.
So please navigate and follow your own strategic plan, but it's really interesting and useful to analyze orbitals, and also it is critical. It's not just interesting to practice the Ferrier command.
Yeah, when we say Furry, where does that come into this place when I have? Because I just explained what I thought. I guess I haven't edited this since the first time we talked, but is this going to be, Furry was going to be its own category, let's just say in the columns, or its own category in its row? So like
let's do at least one more column for Ferrier.
There we go. Okay.
And your table will become bigger and bigger, will be pumping up as you go through the project. It's not only putting X for completion of some steps, you realize additional dimensions.
That's fine. That's good.
I
just need to know. It's you got to start off somewhere, right? So good. Okay.
So, anything else you want to say or ask?
Yeah, like I said, I know you're a busy guy, and I keep sending you emails, and you're more than happy to help, which is awesome. I just didn't know if there's like a student, like I can literally run to whatever your office is in the chem department, and there's a student there who does this. I could just talk to them for an hour, clarify some things, and get out of there. I didn't know if there was an opportunity for that.
For this project, there is only Dr. Han who knows the procedure because he's the developer of the method. And you are currently the only student who is doing this project. So if you need just to plot orbitals or spectra, then feel free to ask anyone. But for this Fervia and excited state dynamics, let's keep interacting, and at some point we may interact with Dr. Han as well.
Okay. Thank you for clarifying.
Dr. Han, do you have any questions or suggestions to me?
Is there any justification for the atomic models?
For the models?
Yes.
Are you saying the specific polymer used, or are you saying like conformations that I've chosen?
Like in general, how much vacuum did you put in your system? Is it periodic?
Oh, see, yeah, those small details. I'm still learning along the way. I'm actually using a lot of the programs or code that Dr. Keelan is prescribing me, and I'm trying to run it and kind of learn as I go. And I couldn't tell you that off the top of my head.
Okay.
So me and Professor Keelan, are you going to investigate just one system in this step?
So by today, we have about 5 systems.
5 systems.
Yes, and it is not a limit. We need to get some moderate success, at least with few, and then we can expand further. So the 5 systems are as follows. The first one is what Mead was exploring when he was doing the class. There are some doubts, but still it is one of the systems, and we can keep exploring it. Then there is so the model that Mead was exploring in class is kind of planar and extended. And I want to bring up that this project was discussed between Dr. Han and Dr. Jayaraman Sivaguru, like in 2015 and 16. It was a long-term plan to make this simulation, but we didn't have enthusiastic student who may invest time in it. So Mead's help is really useful. And in the first stages, in few years ago, and in the project in class that Mead was doing, the model was just hand-drawn in a planar way. When we decided to revisit this project, I did some attempt that later Mead can redo, and we all can retry. I took this model and let it to optimize with universal force field for like 30,000 steps.
Okay.
So quite long. I expanded it to be a oligomer of like 6 units, and let it optimize really long. And then it started like from planar, it developed kinks, bends, and it's now very much not planar, but the total energy is much less. So because this polymer is consisting, and Mead was showing it in the schematic diagram, of 2 units: the nitrobenzene and furan with some carboxylic groups. So this these two parts are conjugated, but their connections are not conjugated, and therefore these units are planar, but the connection between is not. In this force field optimization, it's close to 90 degrees, and it goes like zigzag, one another, one another.
Right. Yeah, I see. Me is showing that. Yeah.
Yes. So.
Oh, you guys can see my. You guys can see my screen still.
Yes.
No?
Yes. Yes, we can.
Yeah. So that one. Yep.
Yes. Thank you, Mit, for showing it. And on the right side, there is one more model. So this one has a period with the kinks occur each fourth bond. So it's like nitrobenzene furan, nitrobenzene, and then kink. Then furan, and then kink. So it has a long zigzag. And there is another model with quick zigzag where kinks happen more frequent. Those are two isomers. By composition, they are absolutely identical. They have different conformations, and in order to have the same number of atoms, Mead has two models. One is this long period, which we call dimer, and another is monomer times 2, which is the frequent kinks. But it is this frequently repeating unit cell is repeated twice. So long period and 2 short periods with vacuum. So running these two isomers and exploring these two isomers is a good setup of a problem for me. In addition, one can explore this short model with only one period with vacuum, and the short model with water added there. Because it will be too many things, let's keep it away from Mead's focus for the time. And I am trying to explore these models myself, and I will deliver something in a few minutes. So I put effort in the monomer with water, and the monomer with vacuum is still not explored. Maybe we will rotate tasks between all of us, and it will be done with time. As we discussed on our last meeting 2 weeks ago, the next possible step is to squeeze more than one threads in one unit cell, to have no vacuum, no water, but densely packed threads of this polymer at the density corresponding to a realistic situation. And this is not for right now. This would add complications, because still there are not many people who are doing it, and if we try to do everything, we can lose steam and achieve nothing. But after getting, maybe in like several months after getting moderate success, if everyone is happy and we are getting some reasonable results, we can go into the densely packed polymers, where expertise of Professor Rasulov and his group can be really helpful to create this gravimetrically correct densely packed models.
I see. Okay.
Okay.
Thank you.
Okay. So are there more questions to Mead or suggestions? Okay. If no, I would like to ask you permission to present myself. And thank you. So in a minute I will start sharing screen, and I'm not claiming final and best possible results. It's only an example what Mead could do. So he is asking questions, and maybe some of these practical steps that I will show will be answers on the questions that Mead hasn't asked yet. And also, I was trying anytime I was sober to put the it's a joke to put the link to the path to the files on the Quarry cluster. So if any of collaborators want to look on it, especially Yulun, you can just look and play with it. And also, I'm giving explicit examples of the oscillator strengths file contents and explicit examples of the Fairview command. In addition to Mead's effort, we are asking some expertise help from Professor Rasulov in arranging scripts. And these two sets of data are important components of the script, so I will show them through this mini presentation.
Mm-hmm.
Okay, so there is a plan to achieve some results and present it on Pacificam, and there will be several points in this presentation. So starting from minimal experimental background, open challenges, summary of main results, which are main parts and should be sufficient, and then a little bit of technical details, which will take like 60 slides, but main message is in summary of the computational achievements. So we all are inspired by the paper of Siva, of Dr. J. Raman Sivaguru, and the idea, the motivation behind this paper is that one becomes extremely environmentally friendly. So one creates plastic bottles for packing, for water, that after use, one just throw it up to the sky, sun shines on them, and they decompose and do not create any waste. I'm a little bit exaggerating, but it is a main idea. And this paper is communications. It's very brief. But in this in addition to this 4 pages paper, there is a very extended supporting information, which has it's like a book. It's really inspiring reading, and it has, for example, some things which can be natural for people in Department of Polymers and Coatings, but for me it was like discovery. So they consider polymers closely packed with polymeric material only, and they also have polymeric materials with a little residual water between strands. And they find that they decompose in a different way, giving different reaction products. Also, in this paper, they extensively characterize reactants and products of this photoreaction by several means, including infrared vibrational spectroscopy, NMR spectroscopy, and UV visible spectroscopy. Right now we are focusing on the UVVs, but it is also possible for us to refocus on the vibrational spectroscopy. Our software engine, the VASP, and many software packages do have this option. It's not a big challenge. So, to my understanding, which is not guaranteed to be correct, but this is the main achievement, main result of the paper. So they have a polymer formed of repeating units of this class, and this material is white or transparent. But after being exposed to UV irradiation, it becomes more brownish. And bonds between carboxylic group and this nitrobenzene, and there is also one CH2 here group. So these bonds are being broken. From the point of view of spectroscopy, one can interpret it as absorption spectrum having maximum in the beyond visible in the UV range, here moves into visible. And they repeatedly see this pattern from UV to visible, from UV to visible. So we cannot plan to get absolute coincidence in all tiny numbers. First, we need to get qualitative agreement with experiment. And our main criterion of success would be to see red shift of spectrum upon photoreaction. Okay, done with experimental background. The challenges are to identify the mechanism, which bonds are broken, which is it the same products for any wavelength excitation, or one can control the products of the reaction by changing intensity and frequency of the wavelengths. Also, it is not known about the mechanism, like what should be the nature of the orbitals contributing to the photoexcitation in order to get quickest possible degradation. So mechanism and specific wavelengths that parameters of the excitation that lead to degradation. And in this model, which is monomer with water, I need to make a little disclaimer. So it is a periodic model with periodic boundary condition. And therefore, to represent infinite model, one takes small fragment with understanding that it is being repeated again and again. So the fragment in here is being repeated, and the bond that I have highlighted in red, it is identical here and there. So this furan group has carboxylic, so oxygen, carbon, oxygen. No, not this one. This bond is periodic. I apologize. Let me erase the one that I don't want. No, this one is periodic, and the one that we do need to, well, hypothetically we expect to break is the bond between the oxygen on the furan group and carbon that is a linker leading to this nitrobenzene group. Anyone is welcome to correct me, because I do not have chemical background and can call compounds in a wrong way. So we are going to specifically focus on these bonds that are highlighted by cyan and green through several manipulations. But since this model is immersed in water, there could be, we hypothesize that it could be borrowing or donating hydrogens or oxygens from dissociated water, leading to more rich chemistry compared to vacuum or standalone packed polymer. Okay, so what are we getting through the modeling? I'm going to show main result and if it would be like 5 minutes or 10 minutes talk, it would be the end, and then there would be technical details how to arrive to these results. So in a very summarized way, the top line shows experiment, so breaking bonds, or I've learned from Mead that one can use advanced word cleavage. So upon breaking this bond, the spectrum moves from UV to visible. In the modeling, and those are not atomic models that being experienced in dynamics. It's after completing the modeling, the product is converted into this chemical structure by Babel software that we will use at some point as well, because this Babel software later on may help to get the mass spectra. So one goes from periodic starting here, ending there, periodic structure to the broken fragments. And on one side, this group converts into CH3. The nitro group loses one oxygen and becomes NO in the trajectory that was computed. And the second group, this connecting group, CH2, is converting into aldehyde group, CH with double O. And the furan recombines back to what furan with two carboxylic groups, so it stays intact. The spectrum before simulation has lowest transition at 500 nanometers, and this is a little like 200 nanometers more redshifted than experiment, but this is done by PBE functional, which is expected to have consistent shift down in energy. And qualitatively, after conversion from reactant to product, we are getting peaks that are substantially redshifted, with lowest peak at 1100, so about 1 eV. So the hope is, if one recomputes it with more reliable hybrid functional like HSE, the gaps may come into better agreement with experiment. But this spectrum corresponds to red line on experiment, and this spectrum corresponds to one of these long exposed lines on experiment. So qualitatively, we are getting the red shift, and the same information is obtained, can be seen even before doing the spectrum by analyzing the density of states. So before reaction, it's about 2.5 eV, and after reaction it's about 1 eV. Let me highlight once again that these components are not hand-drawn for subsequent analysis of electron structure. It is meticulous procedure of modeling reaction. So this is not drawn by hand, but automatically forms through TDESMD procedure from the periodic structure. Okay, done with main results. Feel free to stop me anytime and ask questions. And if there are no questions, I'm going. Please prepare.
Yeah,
Yes,
I do have one.
please do.
You said that that redshift trend can be seen just with the density of states.
Yes.
Okay, can you explain why that?
Because
Smaller
one
gap or
because
larger gap?
because one is smaller than 2.5.
Yep.
Yeah.
So what is? Yeah, but I mean, to me, it's just a smaller gap. I don't know why that would indicate a red or blue shift or anything like that.
Increase of the gap is called blue shift. Decrease of the gap is called red shift.
Okay, that's just something I should know.
Yep.
Okay.
Well, I have a question.
Please.
I have a question. So this photo cleavage and splitting to these two particular compounds is kind of the manual step, or it can be predicted by the simulation. So
It
this
is. Thank
particular
you.
compounds.
Thank you for asking. It is predicted by simulation. It is not manual. It is not manual. It is not manual. So it is a black box, or at the black box procedure, computational code. At the input, we provide original structure and wavelengths. At the output, we get final structure. So it is a predictive power.
Great.
It's the product is function of the wavelengths of excitation. And before running simulations, we do not know what will come out. So
that's great. That's what I wanted to hear.
Yeah, exactly.
We don't
And
know, we have no idea, and the simulation actually gives us the answers. Right.
well, we can justify simulations by comparing them with experiment. And for the absolute values of the gaps, it is a standard shortcomings of ODFT, and there are standard ways to fix it. I just was lazy and didn't invest enough time to fix it because rushed to get some qualitative trends. Also, if, again, it's all many ifs, but if we all keep staying happy, if we get positive results again and again, at some point it would be really a great dream if you apply QSAR or any other cheminformatics methods to mimic like this black box converting wavelengths into products. It is, in the best case scenario, it is like 24 hours of calculations. It cannot be done shorter. And if you do some fitting protocols and use this wavelengths as a parameter, one can get it in seconds. Like train.
Train the model, the big model on, let's say, a number of data points, and then, yeah, if it will be able to work this kind of model, that would be great. So we'll see. Yeah. Right now,
we can write. I don't know how soon we can do this calculation, because before one needs to accumulate a lot of trajectories, a lot of training set data. But as a proposal, we can start writing it right away. Okay.
Why not? Yeah. That we can discuss later, just in between us, right?
Okay.
Okay.
So let me then continue. So technical details. Please buckle up your seatbelts and prepare for about 60 slides of technical details. Main result is already reported, and now it is more like demonstration to Mead what is expected from him to do. So these technical details have several subsections. So density of states and orbitals, spectra and analysis of oscillator strengths, movies of TDESMD dynamics, snapshots of the dynamics, and then fifth, the spectra of the products. In some sense, we already looked at number 5. And in order to reach to the last step, we need to start from density of states and orbitals. So the model here is shown on the background, and orbitals are labeled and shown in blue clouds for occupied and red clouds for unoccupied. And each orbital corresponds to each place, each peak on the density of states. So Luma plus 1, Luma plus 3, Luma plus 4, and for this Homo minus 1, and so forth. So before we go into composing pairs of these orbitals and exploring the dynamics, we need to look in more details and make some intuitive analysis of the shapes of these orbitals. One can, if you would do a paper, this figure standalone will be enough, but I'm going to refocus on orbitals one by one, starting from lowest to highest in a range, and I will try to speak a little bit about each orbital. So here is the file states that Mead is aware of, because he was doing the density of states, right? So first column is number of orbital, second column is energy, and the third one is occupation. And one identifies where is Homo and where is Luma by looking where this number 2 converts into number 0, right? Good. So let's look on the first in a row, Homo minus 30, and I symbolize it by arrow number 3. So the orbitals are three-dimensional, but it's too hard for humans. We are looking on a planar figure, and even here is the density of the orbital projected on z direction. So where the cloud of orbitals has maximum, there is a peak here. When there are no orbitals at given z value, then there is a dip. And this is not necessarily, but it helps to analyze the orbital. So this Homo minus 30, which is I-134, what can we tell about it? So it looks like there are carbon pi orbitals on in the conjugated way, and likely pi bonds. There is a density on nitro group, and there is a density, covalent density between nitrogen and carbon. There is charge density of on carboxylic group, and it's frequent, since here is the water box, there is a charge density on oxygen from water. I'm going to do the same analysis for each orbital. It could be quite boring. So next one, Homo minus 21. I skip boring orbitals. So Homo minus 21, it has much less pi conjugated on furan and nitro group, but here it has a pi orbital on nitrogen from nitro group. It's interesting, and also charge density on carboxylic group here, as well as on the water. Going next, Homo minus 13. Again, it has substantial density on the nitrogen from the nitro group, and it has density on the one of the carboxylic groups, and the rest are on waters. Going further, Homo minus 12. Now oxygen from nitro group, and the most other things are on the oxygens from waters and oxygen from the furan group. Going further, we are done with about half of the orbitals. I appreciate your patience. Homo minus 6, a lot of density on the nitro group, and some density on the surrounding oxygens. Nothing on carbons or carboxylic.
I have a question now.
Please do.
Yeah, so like, okay, maybe you've said it, I'm just missing it, but I mean, I see all these peaks on the bottom left graph, and so are we going to assume that the largest peak, I believe it is HO minus 13, is actually going to be like the transition state that we were talking about from HOMO to LUMO?
So notations. I'm going to flip 1, 2, 3, 4, 5 slides back.
Yep.
So here is the list of orbitals. 164 is the last occupied, so we call it HOMO.
Yep.
Then 163 will be HOMO minus 1.
Yeah, no, I get that. Yeah,
Okay.
all the way up to minus 13. I'm just saying, like, the peak of this density of states, to me, I would assume it means some significance relating to like a transition. You know, I know we were explaining how HOMO minus 13 could go with LUMO plus 5, and that would be kind of the thing that we focus on in the furry.
Okay, I got what you're asking. You are practicing healthy impatience. Before we go to transitions, we need to invest a little time into exploring each individual orbital, and it takes time and effort.
Okay.
Yes, but yes. After we go over the list orbital, we will compare their pairs and look which orbitals are best candidates to induce transition.
Yep. Okay.
Going further, HOMO minus 2. It looks very nice pi orbitals on carbons of benzene, and you see here they form bonding here in this region. It's good bonding orbitals, and also some pi orbitals on the. It's also conjugated ring of furan composed of the bonding orbitals. So it looks like. HOMO minus 2 seems a good candidate because of this conjugated bonds. It's a good candidate for participate into optical absorption and induce fragmentation. Going further, HOMO minus 1, it has this pi bonds on the ring of the nitrobenzene and on the nitro group of nitrobenzene, but nothing on furan. So maybe it may participate in selective excitation of the nitrobenzene only.
Nitro.
Yes. Going further, HOMO, it has some character as before, like a little bit on each part of nitrobenzene, plus some density on the furan group and the carboxylic. So it looks like homogeneously distributed on this polymer. So it may or may not contribute. Nothing super good, nothing super bad. LUMO. I'm very surprised. I'm not sure if we will see the same trend in other models. Here the LUMO is on nitro group only. The surprise is because oxygens are electronegative and typically they are occupied. So I would expect this orbital being occupied, but maybe through dynamic equilibrium with water, something happens and there is a lack of electrons. So this oxidizing group is missing electrons, and then it will pull it upon excitation. I don't know. It's a little strange. Going further, LUMO plus 1, it has the orbitals, pi orbitals on the carbons that link furan and carboxylic group. I don't know how to interpret it, but it is like continuing conjugation between furan and carboxylic. We are close to the end of the list of orbitals if your patience is expiring. The LUMO plus 2 is composed of the pi orbitals on carbons on the nitrobenzene and pi orbitals on carbons on the furan. But since they are unoccupied, they have anti-bonding character. So this pi orbital here and there, and instead of having shared density, there is a nodal plane between these carbons. So this LUMO plus 2 orbital seems to be in a good coincidence in pairing conjugated to HOMO minus 2. And because it has this delocalization over several pi carbon atomic orbitals, it is also a good candidate to participate in the optical excitation. So the charge density in HOMO minus 2 and LUMO plus 2 are localized on the same, they have spatial overlap, they have this bonding to anti-bonding transition, and it's a good candidate for both noticeable absorption and for good reason for promoting reactions. And few more orbitals higher up, LUMO plus 3, it has anti-bonding on nitrobenzene only, so it may pair with HOMO minus 1, and the LUMO plus 4 also has anti-bonding on both nitrobenzene, furan, and carboxylic group. So LUMO plus 4 also may contribute to the transitions. And this is a summary. So if you would do a paper, one can show only a figure like that and then describe observations in the figure caption and in the main text. Okay, done with the section on density of states. Now spectra. Here there is a, on the left panel, there is a portion of the oscillator strength file. Right now, we do have an applied meeting. We do not look onto like equations and principles, but basically this oscillator strength is includes square of transition dipole between each pair of orbitals dij, and the transition dipole is nothing but matrix element of the position operator.
Hey, Dr. Razalev, could you mute your mic?
Yeah, just a second. I will see.
So,
Just take your time.
what one should look into this one should explore in this file. First, there are more columns, but first 4 columns are more important. So, first and second column are unoccupied and occupied index of orbitals. So the very first shown here is HOMO to LUMO. If you look before into our list of orbitals, one opposite, occupied to unoccupied. Occupied to unoccupied. So 164 corresponds to HOMO. 165 corresponds to LUMO. The energy difference between HOMO and LUMO is 2.5 electron volts. And the intensity, the probability that after irradiation at this frequency, the excitation will happen is proportional to this oscillator strength number. So if we look onto absorption spectrum at the 2.5 electron volts, the height of this peak corresponds to this number. 0.6 will give us height of this peak. Then we, if we arrange transitions according to the energy, the next transition at 2.7, so it's from HOMO minus 163 to LUMO. And it has a little bigger energy, 2.7, and about twice as bigger intensity. So the number is different color. So the probability here is responsible for this tall peak at 2.7 electron volts. And then for each pair of orbitals, we compose such a transition. And here we just label it because we need to look at this map of transitions and orbital indices again and again. And very soon, this map of transitions will serve us as guide for formulating Fermi weight string. I hear some sounds which may mean questions. No? Okay. So this in this subsection we have only one slide, but it is quite important. So we are done with optical spectra and analysis of oscillator strengths, and we are going to the next movies of the TDESMD dynamics. I'm going to play some movies, but I'm not sure that transmission is good enough. So I'm going to share the links to YouTube, which you may watch if quality of what I'm presenting is not sufficient. And first few movies will be boring. You can skip about 3 of those, and the number 4 that I will share will be very, or maybe number 6 will be very interesting. So let me do this little preparation and share the links, because these movies are often delayed by transmission through this communication software. And if you play them on the personal equipment, it will be much higher quality. So total 6 movies.
So I don't know. I can see you sending it in the chat room, but it says requests to the server have been blocked by an extension. So like we're not getting any links actually. In this little chat.
We're not getting links actually.
You're not getting links? Okay. Let me then run it over and send it as an email to everyone. I know it's a little boring delay, but it will be very pity if I start explaining movies and no one can see what I'm showing. So while I'm preparing this transmission, I can just briefly explain what is going on. So the information from oscillator strengths file is converted into so-called Fermi string which is the key portion of the TDESMD algorithm. And the TDESMD algorithm is practiced with different Fermi strings, which gives, and at the outcome of this black box, the trajectories of the photoinduced dynamics. So the little disclaimer, when we were discussing with Professor Rasulev several minutes ago, I was telling that it is a black box that gives products. In addition to products, it gives all intermediates and transition states. And this intermediates and transition states okay, just three of us. Movies. Okay, so I believe that if you should get this links, and they should run in the on your equipment if something doesn't work here. So I start from the simplest HOMO to LUMO transition. This HOMO to LUMO transition is encoded as Fermi 163 times 1, then 0, then 1, and then 59 times 0. One can replace this recording if one wants to do numerical style of saving by just making a string of 1 space, 1 space, and 163 times this much. Then after that, doing this inversion 0, 1, and then space, and then again 0, space, 0, until one gets necessary number of zeros. The total count of occupied orbitals is 163, and total number of orbitals in this model is 224. And this information of number of occupied orbitals and total number of orbitals is extracted from the outcar. And it is a standard information that we do naturally by grabbing it from outcar. It is not a problem. Those are input parameters. But creating this string in the automatic way as a function of the wavelengths is a little challenge that currently we do manually. And it would be really great to do it in the automatic way. So human just gives number or sets a number, funnels number as an input parameter, and then the code works automatically to minimize human input. Now,
so then a question in this regard, Dave.
Yes.
So human only gives kind of the command at the first step, and then everything happens automatically, or every time at every calculation the human should identify this particular the excitation energy, which needs to be then taken and converted to the Fermi file.
Thank you very much. It's a perfect question that we all were thrilled for years. There are three levels of calculations. First, one just promotes system into excited state and runs excited state molecular dynamics. This can be done by WASP without any novelty. Second option, we apply the unique TDESMD procedure for flipping excitation between ground and excited. But it is the same ground and the same excited along the trajectory. It is what is done and published, and it is where you have contributed to the papers. And the third level that no one in the world has implemented, and it can be a terrific novelty, if we change the which excited state we use during the trajectory.
During the trajectory?
During the trajectory. So it should be completely automatic, because even the very fast human cannot compete with HPC cluster and change parameters as things are going.
Mm-hmm.
So
there should be some kind of artificial intelligence which will decide what excitation energy to check and quickly.
No. The algorithm will be absolutely the same. One just recomputes oscillator strengths and selects the maximal transition and uses this pair to encode Fermi string.
Oh, okay.
So
okay, got it. So yeah, that's relatively simple. Right.
That's relatively simple. I would do it in Fortran by using format command and writing long line, but maybe there is a more elegant way to do it, platform independent, like in Perl or like a script, a shell script. Okay, so I'm announcing 4 boring movies, and then there will be 2 really exciting. So first, boring movie. As time goes by, we perform excitation from this orbital. Oh no, it doesn't want to let me movie.
No, I see the moving. I see moving.
Okay. So as movie is going by, I'm looking myself on the right panel with HOMO and LUMO inserts, and this motion, we start from 0 Kelvin, but we get system ramping up through temperature by exciting it from HOMO to LUMO, which are localized on slightly different fragments of a molecule, and then the bonds are contracting and expanding and distributing through non-linear molecular interaction to other fragments. And as time passes by, system gets hotter and hotter. But for this specific excitation, all chemical bonds for the backbone remain intact. We see formation and breaking of the chemical bonds between waters, but it's more like hydrogen bonds. So the water box is dynamic, and they approach and depart each other and keep this network. The line, right now we see 7.7, it's not a true bond, it just shows when atom goes across periodic boundary condition, we should interpret it as the bond goes stays intact. You see it's flipping, forcing back. And to not to expire your patience, I'll just quickly go maybe to the end step, and we see that it looks a little bit corrupted, but all groups, all bonds are intact. There is a furan group, there is a nitrobenzene, and all bonds are in place. Let's keep going into different excitation from HOMO -1 to LUMO. So there, let me bring attention, there are 162 orbitals occupied, then one unoccupied, then one more occupied, and here is the Fermi energy, the border between originally occupied and originally unoccupied. And then this one is LUMO, we have LUMO occupied, and then the rest of orbitals are empty, 59 times 0. So if we, and it corresponds also for transitions between nitrobenzene and nitro group only. So we see right away that it activates the oscillation between nitrogen and carbon in this nitrobenzene group. And then in a chain wise, this amplitude of oscillations is distributed through the whole system. But if you follow it, it still does not get too far. I'll just scroll to the end. So it looks corrupted. Some bonds are corrugated, but still backbone remains the same. Carboxylic groups are connected to the nitrobenzene. Same situation if you look from HOMO -2 to LUMO. So it's also from nitrobenzene and furan to nitro group. And if we run dynamics, each of the dynamics look differently. It's also oscillations of carbon to nitrogen. But if we follow to the end, it twists it in a different way, but it doesn't change its chemical identity. All carbon-carbon and carbon-oxygen, carbon-nitrogen bonds stay the same. There are a few excitations that are still in the queue. So HOMO -1, HOMO -6 to LUMO. If our meeting would be like a week later, they should be available. So scanning through all available peaks in the spectrum, and then there are a couple of peaks that are more to the further to the UV range. So here we are looking from HOMO -1 to LUMO +3. So here both occupied and unoccupied are localized on the nitrobenzene group, and one would also expect that it should activate the bond between nitrogen and carbon. Let's see how it happens. So even for very successful simulations, nothing drastic happens for the first picosecond, for first 1,000 steps. Noticeable dynamics happens after about 1,000 steps, which is about half of this trajectory. And this movie is about for 2 minutes, and you see that several bonds are experiencing high amplitude of oscillations, such large amplitude that sometimes it is interpreted as broken bond, and then they regain back, but it is on the limit where system is about to decompose. So with such a large amplitude of oscillations, it's becomes less stable. And it's still, now you see carbon to nitrobenzene did steal oxygen from the furan group, and right now you see that it becomes complete soup, like a plasma of the smaller fragments. So it means this excitation wavelength is very efficient to transform photo energy into chemical energy, into bond breaking. And right now there are something that looks like a cycle from nitrobenzene, but furan is completely gone. It's transformed into something wild, which means at this wavelengths, the energy is transformed very efficiently, and it will definitely decompose. Maybe here in the algorithm we are exaggerating the intensity, and in the real situation on experiment, it would correspond to much longer excitation with higher intensity. Typically, they see on the first instance of breaking the least stable bonds. Okay, two more left, and the last one will be most interesting. So we saw two. Yes, please.
I have a question.
Please.
Well, actually, not a question. In your video in particular, it stops at like 1 minute 42 seconds. Is that your choice, or was it not meant to do that? Because it's like a minute of it not doing anything.
I understand the question, and I do have the answer. I'm just finding the right words. The duration is implementation of what we discussed at the beginning of the meeting. One requests certain duration, but computer system allows only so much wall time. And depending, if we are exploring system close to equilibrium, calculations go quick. But if we are looking some exotic transition states, it takes much more time for each ionic step, and it takes longer, and we didn't progress as far as in other simulations. But to be consistent, all movies are set to the same duration, but this one fit only about 1,500 femtoseconds, and it already leads to this drastic decomposition. Does it answer your question?
Yep.
Okay. So second last from HOMO -1 to LUMO. So it's HOMO is on the nitrobenzene, and LUMO is shared between nitrobenzene and furan. And we do see that carbon and oxygen from nitrobenzene and carboxylic linker experience high amplitude elongation, but they often regain back. So it's a sequence, and after some period of time, no, they regain again and again. That's right. And this effect of repolymerizing after some times is mentioned in the paper by Dr. Sivaguru. So if one excites the model not long enough or not at the right wavelengths, it may depolymerize and then polymerize back. And I think we can interpret this simulation in this way. So it gets enough energy, but not enough to break bonds forever. And the last movie for today, but it will be the most interesting one. So we already identified that the orbitals HOMO -2 and LUMO +2 are special. So in these two orbitals, the charge density is delocalized over all conjugated sp2 chemical bonds in both nitrobenzene and furan. And it is a good candidate for excitation, and we may expect that it will homogeneously distribute like strain and activation induced by photoexcitation over the whole string. So let's play it. If you are not watching what I'm showing, but playing it on your own computer, it should be the last link. So I'm specifically looking onto the carboxylic group connecting to the nitrobenzene, also on the nitro group on nitrobenzene, and also I'm looking on the this CH2 groups that are connecting to to the carboxylic groups. Some of these groups are candidates to participate in giving or accepting hydrogen or water from the soup of dissociated waters. So we see now that carboxylic to the CH2 groups again play this game of elongating and rebinding, but for the central group, you see number 3.2 something. It carboxylic to nitrobenzene group has broken and doesn't regain back, and we see that there is a it also did pick the water, one oxygen from the water, and this prevents this carbon from rebinding back to the carboxylic group. So this model seems most reasonable and successful. It's not super vivid, but it shows formation of two major fragments. One is furan with two carboxylic groups, and another is former nitrobenzene, which is slightly chemically modified. So by optimizing this this model, which Dr. Han has named in our common paper, we call it cool intermediates. So if one takes cool intermediate or cool product of this trajectory, which is located in the there is a link on the bottom, then one is getting this density of states and absorption spectrum of the product, which is the main result. Now, I am asking you permission to go over the last video once again, but we will go over it not as a video, but we will look over snapshots each 100 femtoseconds. So we will look most important steps. So instead, totally this video takes about 2,500, 300 femtoseconds, and we will look only each hundreds, like 0, 100, 200.
Sounds good.
Okay, buckle up, prepare your patience. So time 0 femtoseconds. Bonds, carboxylic. Here I think I can make drawings. So the bonds that we are looking at, this one and this one, are intact, and everything looks good. Go to 100 femtoseconds, the bonds are intact, system goes well. 200 femtoseconds, bonds are intact, nothing interesting. 300 femtoseconds, all is staying stable. 400, bonds are in place. 500, bonds are in place, and this carbon is connected to by double bond to oxygen and by another oxygen here, and it is this carbon. So we need to interpret it as connection through periodic boundary conditions. 600 femtoseconds, still carboxylic group in place, carboxylic group in place. All bonds, polymer is still a polymer. 700, still polymer, stays polymerized. 800, polymer stays polymerized. And we just see this carbon moves forth and back through periodic boundary conditions, but it doesn't mean that anything breaks with this carbon connected to this oxygen and this oxygen. So going further, 900, all good. 1000, it elongates a little further, so it's like 183, but still it's high amplitude oscillations which regain back. We shouldn't consider it as a bond broken, because any optimization will bring it back. 1100, still oscillations between this carboxylic and CH2 groups that belong to nitrobenzene. But we are approaching to the instant of time where chemical transformations will start. 1200, we see this bond regain back, and we see a little bit more twists and changes. 1300. So it is still intact, but you see the hydrogens on the linker group become more, gain more higher amplitude, and they are approaching closer to oxygen, which may lead to chemical transformations very soon. Now, 1400. We do have the central bond between carboxylic group and this CH2 is elongated long enough, like about twice, so 2.5, 2.6. It's highlighted with green. And then we do have linker group CH2. Originally, it was CH2O, and the carbon was in the sp3 hybridization with surrounding. Now it is in sp2, which could be not as saturated. I'm not sure if I'm using the right words. Not as stable, and is more ready for chemical activity. And the second carboxylic to linker group is intact. Here there is a bond. It's just not drawn, but it's still here. Now going to 1500. The connection between carboxylic group, central carboxylic group, and the CH2 linker stays elongated. It doesn't regain back, and high amplitude motion of hydrogens, they create like a barrier. This hydrogen doesn't know if it wants to be attracted by the oxygen from carboxylic or return back. And this linker group stays in the CH2 configuration, which has potential for chemical activity. Also, the second carboxylic group at the top left also breaks this bond, like elongates to the distance where we have doubts to call it a chemical bond, but it may regain the bonding back. So we are more than half through. If your patience is limited, we'll be done soon. 1600 femtoseconds. The central one to carboxylic group stays broken. The second one on the top left regains back. So right now it is like in polymer chain only one bond is broken, but the rest of things are still connected. Keep exciting it further. 1700. So a little bit more developments. So the distance from carboxylic to linker group increases, and now this carbon picks up an oxygen from the solvent. There is a bond to oxygen, and at the same time there forms the H3O plus group, which probably compensates the stealing of oxygen by our nitrobenzene. The second carboxylic to linker group breaks once again. Then this linker group comes into CH2 configuration, which probably means double bond here. It's highlighted by yellow, and it shows that it's chemically more active. And also this purple highlight the nitro NO2 group gains higher amplitude motion, strange angles, which means it is also activated and ready to participate in chemistry. 100 femtoseconds less, 1800. The carboxylic to linker group bond doesn't regain anymore because this additional oxygen, and we can identify it as aldehyde, like C double oxygen hydrogen group. This hydronium H3O plus stays nearby. The second carboxylic to linker group regains back, so I think it teases us, it breaks and reforms back. And the nitro group did lose one oxygen into the solvent and gets NO with some hydrogen nearby, which probably this hydrogen is just a guest which will visit and depart soon. 1900 less, the primary bond between linker and carboxylic stays broken. The second carboxylic to linker stays connected, and the nitro group has transformed to NO or maybe NOH group. A few steps more, we are close to the end. 2000 steps, the central NO carbon to carboxylic stays broken. Aldehyde group stays as it formed. It looks like it is stable. NO group in place of former nitro group stays. And the last carboxylic to linker is not yet broken. 3 steps more. 2100, the original linker to carboxylic is broken and will never come back. Nitrogen to oxygen group stays the same, and second linker to carboxylic breaks once again, hopefully for the last time. The linker group stays in the CH2 format, which means it is chemically active. 1200. This one regains back, but let's see what it does in the very last step. In the very last step, the carboxylic to linker stays broken. The secondary carboxylic to linker breaks again, and it picks another hydrogen from the solvent. So now it is in the CH3 format with sp3 hybridization, which looks much more stable and will not break upon optimization or further reaction. And then we are done with following the molecular dynamics. So the last step is analysis of reactants and products. So this is the same model plotted with different software, Vesta, so it automatically helps to expand beyond the boundary conditions. So our model is in the central area, and here it draws lines how it continues for this zigzag stuff. And below there is the same model after we are done this TDESMD, excited state dynamics. So the nitrobenzene group converts into this standalone group, and furan with carboxylic group also stays furan with carboxylic groups. But there are waters between them, and the terminating groups are passivated by like CH3 and aldehyde group, so that they are not chemically active anymore, and they're separated in space. So those is a demonstration of depolymerization from continuous polymer backbone to standalone units. And further to the right, there is a density of states. We were already seeing it. So with wide gap and narrow gap before and after simulation. And we also see the spectrum in the nanometer argument with a red shift going to more to the larger wavelengths. And if we take the reactant and product and convert it with Babel and convert it into chemical structure, it looks this way. So CH3 group on one terminal, aldehyde group on another terminal, and NO2 converts into NO group, while the this carboxylic decarboxylic furan gains back. So red shift means darker beaker with some brownish substance, while before reaction it is white. And here is the slide where we started from. So by cleavage of the bond, we are gaining red shift of the spectrum as in qualitative agreement with experiment. And as a conclusions, one can say that the mechanism of this reaction is by exciting the orbitals, the pairs of orbitals, both of which are conjugated along pi-pi conjugation over both units. And another important part of the mechanism is borrowing and donating hydrogen and oxygen from the soup of dissociated water, which there are expectations that if one repeats meticulously the same procedure without water in a vacuum or in the compressed environment, the products are likely to be different. So we will have two options to control the products of decomposition, exploring dry and wet polymer and trying different wavelengths of excitation. Okay, done.
How a question?
Please.
How different in time gonna be the calculations with the water in comparing to the dry one? So it's much more time consuming.
Yes.
With water.
It's so when the model is already optimized, it will be just more time consumed, but original preparation is a little delayed. So it was a big headache to prepare the box, because after optimization of the water box with force field, one needs another several thousands optimization steps with ab initio, because force fields it's a good initial guess, but then water forms the network where they all are connected with hydrogen bonds with each other and with the molecule, and it's qualitatively looks different from what comes out of the force field. While the vacuum model goes instantaneously, and it is very good starting point.
Okay, I see. Yeah, but that's very interesting. At least this step-by-step explanation and showing how it goes. Pretty exciting. Yeah, very interesting. Thank you. Yeah, it's going to give a really nice idea of how this mechanism happening, how it goes.
I have a question.
Yes, please.
How many water molecules did you put in the box? Is it consistent with the density of liquid water?
It should be. I was practicing ISIF7 to compress it until zero pressure.
Okay.
So there was an effort to get like realistic gravimetry, the density. And
so there is no tool in your case which will kind of approximately calculate how many water molecules you need to put in the periodic box. You don't have this kind of tool.
I was using Hypercam. Hypercam.
Yeah.
That automatically places waters homogeneously onto 2.2 angstrom from each other, then optimizing and then forwarding it into ab initio. But the goal was to reproduce realistic density, but it's not trivial. And total number, I can check the number of waters as we speak.
Some of my students using the pack mold to pack with the water molecules or any other solvent, but that's right. It's not always ideal. It's not always put the right amount of solvent within the periodic box.
I guess in this case, pack mold does not work, right? Because the polymer is periodic.
In this case, what? What do you say you do?
I guess in this case, you cannot use the pack mold.
You cannot?
Yeah, because the polymer itself is periodic. Right? For pack mold, basically you should have a solid, right? It's basically you put the solid in the middle and you just pack some solvent.
You put some molecule, I mean, whatever you want, and then you're just filling the rest of the space with any solvent you want. For example, water. So that's what pack mold does.
Okay.
So I'm bringing to the screen the chemical composition. So it is about 30 water molecules.
30?
Yes.
So a pretty small periodic box, right?
Yes,
so
yes, it's less than 1 by 1 by 1. The original box was about 11 by 11 by 11, but through compressing it to, so it used to have negative pressure, and by optimizing the size of the box, it compressed to about 9.5, 9.8, and 9, where the last one is the Z direction, and first two is across the periodicity. So without waters, this is small simulation cell that works quite quick. With waters, it works quick near equilibrium geometry, and it delays as soon as one approaches transition state. So the number of electronic iterations for each step grows because there are ambiguity which way to go.
Okay, got it.
I have another question.
Please.
I'm quite surprised to see by the end of your trajectories, the water molecule, at least most of the water molecule is still stable. Considering you got lots of kinetic energy by the end of the simulations, right? So it seems to me water molecules are forming some kind of a network, and this network stabilizing the polymer.
Maybe. Let's look. There are two different things. There is a last step of dynamics, and there is a cool intermediate. So right now I'm bringing up last step of the dynamics, and noticeable part of waters are dissociated. Like roughly half of them are H2O and half of them are OH and H3O, or just standalone protons. But since it is realistic density, we probably, if we would allow to expand, then at this amount of kinetic energy at this stage of TDESMD trajectory would probably be over 1000 Kelvin and correspond to boiling and evaporating and creating pressure. But if we keep it compressed, it's more like critical point where it is supercritical point where the pressure doesn't allow it to go into the gas, and it is in between liquid and gas. Network. The word network would be very much applicable to the ice, to the solid water, where it looks very much like I don't know, silicon dioxide or any solid with regular network or crystalline. With here it's more dynamic equilibrium, because if we pick any selected like oxygen, it will diffuse and migrate through the system. So it's the density and overall distance stays approximately the same, but the position they diffuse.
And another question is, what is the advantage of using a periodic polymer? Why not we use just some kind of a monomer and just cap the terminal ligands?
It's another possibility, but I was very naive and blind in the attempt to just blindly model what is on experiment, to save time on explanation in the introduction. Because if I tell there are approximations, instead of polymer we take monomer, it's too much explanation for if we need to present it to impatient audience. And if you tell like experiment has polymer, we have polymer. On experiment it breaks, here it breaks. It's a little easier to explain. Another motivation, which is more practical, the simulation cell for the polymer can be made smaller than for like oligomer, because through molecular dynamics optimization and through these twists, or how to say kinks in the structure, it is much more dense compared to the planar. And we do not need to keep vacuum or water outside of these terminal groups. So the size of the simulation cell is smaller, and calculations are expected to be quicker.
Okay.
And for our tool, for VASP, it's not a problem to work with periodicity, and we need to use advantage of this chance.
Right, I agree. So it's always better to use the real system like the polymeric in our case than going back to the monomeric state. So if you're able to do the calculation on the polymeric chain using the periodic box, that's always better.
Because I'm just thinking for this kind of system, because in the end we want to compute the mass spectrum, right? So in this case, all fragments are relatively close to each other.
Oh, okay. I see your point. This is a little technical challenge that we can address quite quick. I just practice laziness of not writing the code, but I have a core of the code that will we did discuss it, expansion of the unit cell after each calculation. So at the when we convert movie.xyz to movie_all.xyz, right? In between this stage, we can expand movie.xyz to have it like 3, instead of 1 unit cell, have 3 unit cells in each direction, like having 27. This is quite easy programming, and if we come to this stage, it's very doable.
Okay.
Also about the end product and end observable, it would be interesting and cool to do mass spectra, but it is not what they show on the experiment, because on experiment they have very mild conditions. They do not break it on multiple small fragments. They just break this, cleave the bond, and the supporting information to the original experimental paper primarily focuses on normal mode analysis. So I was thinking about just taking reactant and product and compute VDOS for this normal modes and see the signatures of this monomeric elements. In fact, these calculations for this trajectory are already done. It was just not enough time to plot. More questions? Maybe from
Yeah.
me? Yes?
Well, Joe, could you actually send me this PowerPoint if possible for me to just look at it myself?
Oh, sure. I will send it to everyone. Please be aware that it will be a big file that may come not as an attachment, but as a link to Google Docs or such.
Yep. Okay, that'd be great. Thank you. And then actually, I think it's more of a specific. If you go up to when you were explaining initially, like the pi bonds, I think it was maybe during the videos actually.
Maybe it was before the.
Yeah, maybe before.
Before it.
Cause I think it was first when you showed us the orbitals. You're like, oh yeah, these are pi bonds. Can you explain how do you know that exactly? Yeah, maybe this is the part, yeah.
Let me select maybe the best one. Few more. Okay, here. So the carbon, if it has pi orbital and another carbon nearby, and it has another orbital, and they form bonding, then they look shared.
Yep.
So
it seems like. Oh, go on. Sorry.
So it will be like shared density in this region.
Yeah. So I mean, I see a lot of carbon-carbon bonds, and so it's just odd that you're saying, oh yeah, these are the pi conjugation. Like it seems like those are being highlighted, but there are other options to be highlighted that have that same like density or bonding like that.
Let's explore it further. It's we're just at the beginning of the road.
Okay. Well, so you're just saying because it's a carbon-carbon bond, you're calling it pi, right? It's not
no. We do see this pi character instead of density being centered around carbon, which will be for s orbital, right?
Okay.
It has this two-petal structure going away from carbon and having zero density on carbon itself.
Yep. Okay. So it's the shape. All right. Thank you for clarifying.
We may get disconnected because the reservation was finite, but we can keep talking until this. Just letting you know that it may happen. Disconnection may happen anytime from now on.
have any more questions?
So, Meet, you can go put some of the organic chemistry to us and take a look how these all different orbitals are different between each other. This is just local molecular orbitals theory.
Yeah. No, I do know that. It just seemed odd that he was saying, oh yeah, these bi-pi bonds, and I didn't know if you know, computationally, if there was any like information I was missing. But if it's just the shape, yeah,
there is a shape.
I understand all that.
There are rigorous criteria. Like there is a procar file for PDOS, and it decomposes Kohn-Sham molecular orbitals over atomic orbitals and tells explicitly what are how they're composed. This more rigorous analysis can be done if we do have reason for that, if it is our main or one of the focuses.
Right. Right.
Yeah, but in overall, it's very interesting and very encouraging. This kind of thing, if we will be able to do on, in a semi-automatic way to calculate the number of systems within the short period of time, that would be great. Yeah. So let's try. So I will try to focus on this code this weekend and try to write it. Hopefully, it will not take too much time. So then you guys will be able to do some calculations much faster.
Mm-hmm. Yes. And it may lead to more than one or more than several papers, not only for this system, but
so like it's happened with our previous codes, yeah. So that would be great. Yeah, I'm always happy for this kind of things. Yeah. That's great. Thank you very much.
Okay. And let's not put exact date of the next meeting, but tentatively we may try to meet again maybe in about 2 weeks. Looking on the progress.
Approximately plan for that. Yeah, and I may call you in between time several times, especially in regard of this code. So anyway, I can call you just to ask a few questions if I.
Please do.
Yeah. If I get some kind of misunderstandings. Okay, thank you very much.
Okay, thank you everyone for inspiring discussion, and I suggest we disconnect now.
Thank you, Dr. Killen.
Thank you,
Professor Killen, for a very detailed meeting. Thank you. Bye.
Thank you. Bye-bye.